Good afternoon, professors. I welcome you for the last session on of today's class, implementation of stack in QADT. So now we'll see about stack implementation of stack ADT. As you can see, and these are three additional functions: is full, simply, and peak. So full is used for checking whether your stack is full or not, and the empty is to check whether your stack is empty or not, and peak to find the topmost element present in your stack. So here we have a stack which is of a type integer, which can hold up to 100 elements. So next we have a top which is used to check the topmost element present in the array, and that is initialized to -5. For my stack. If you want, you can use 100 also, but we'll feel lazy to type 100 elements and for checking whether the stack is full or not, right? So in order to reduce that, I just try to have size as 5. And moving on to the main function, so I have just a printf to check which are the functions are present in whichever cases. And here I'm using while loop to make this program run for infinite number of times, and I stop when this default cases, and display 4 is for full and 5 is for empty and 6 is for peak. So now I have in push. You can check here with my top is at maximum index -1. So I can print my stack is full and further insertion is not possible. So stack full condition, which is called as overflow. So stack overflow occurs. If not, I'm scanning. This top is equal to element. Or you can even write this in 2 steps, like first increment your top index followed by stack's topmost element is equal to stack's top is equal to the element. So these 2 steps which we have done in a single step. So this is pre-increment. So which means top will be incremented first followed by the other given operation, because as we check our precedence, so pre-increment and decrement operators has highest postings, right? So this is a binary operator, so which has, I'm sorry, unary operator which has higher precedence. So this is done here. And moving on to the pop, if your top is at -1, this means your top doesn't have any element present inside. So that is stack empty, for which you can say as stack and flow. And to check the element which has been dropped out, can do this. So here I have done post decrement. So this means stack of top will be made use for this particular statement, and after completion of this line, top will get decremented. So this is what is the pop statement is. So we can do this, or you can even have another line of code, but that will be little tedious. So you should have some integer variable which is taking the value of top index, and then you can print this particular statement like printf percentage is top ID, and then you can determine your prop index. If this value has to be returned, you can return the value. And here, if you want to return this particular value, you can directly use return to the of how an element in a stack is popped out. And moving on to the display. So if your stack is empty, you won't be able to display any of the elements present, right? So you can say if top is at -1, which means your stack is empty, and you can print that you can't display any element because it is empty. And if your stack is not empty, you can print your elements from topmost index to 0th index. And this will condition, if your top is at -1, we can just return 1, stating stack is not full. If it is half empty or half full, we can just say like can just return 0, stating that the stack has some space left out. Similar way, you can take for SMP. I have used integer as my return type because here in the main function, I'm calling isFull condition function here. And if it returns 1, I'll just print stack is full. And if the return value is 0, I'll just print stack is not full. So in the same way, I'm using integer data type for SMT function also in order to check this at the main function. So if my top is at -1, I can return 1, else I can return 0. So next is peak. So peak in the sense if the top is at -1, you won't be able to find the topmost element present in the stack because you will not contain any element present in your stack. So for the top is not at -1, I'm just printing the topmost element present in my list. So now I'll just execute this. First I'll compile and run that. So simply if I want to print an empty stack, and I call display function, this says my stack is empty. If I use choice 4, here 4 represents this full condition. I'm checking whether my stack is full or not for an empty stack. So here you can see stack is not full, condition is perfect. So now I'll just try to insert elements. Say I'm inserting 67, 45, 23, and checking whether how many elements of, whether 3 elements are present or not. Yes, we have 3 elements present. So 23, 45, and 67. As we all know, stack employs last and first with strategy. So the last first insert element 67 was displayed as the last element. So now our top will be pointing to this particular value. So even we can just try to do that. So here we can just print top index. Okay. Or even you can check with the peak, right? I'm sorry, I forgot that. The peak or the topmost element present is 23. Even that index can be printed. Just what this and stack again. I'm trying to push and put the elements into my stack. And I'll check how many elements are present. Followed by I'm using the choice 6 now. So 6 represents the topmost element present, right? The element is 23 and the top index plus the third index. So now we'll be able to add one more element. Instead, we'll just try to swap an element, that is deleting an element, and the element prop is 23. So when you try to display it, you have three elements, and the peak, that is the topmost element, is 69. So next you can check for full condition using code choice 4. Stack is not full, it's my stack empty node is not empty. So now I'm trying to add two more elements. I added two more elements. So my stack is consisting of 5 elements now. So when I try to add one more element, you can see this encountering stack overflow error. So now as my stack full, I'm checking if my stack was full, if my stack node is not empty. Now when I try to swap all the elements missing, you can check here. 77 was my topmost element, so that is getting deleted next. So now I'll check is my stack full, stack is not full, and stack is empty is encountered. When you do 6, so that means you're trying to access an element in an empty stack. So it is showing stack overflow error. So this is how a stack data structure is validated. So do we have any doubts in this stack implementation purposes? If so, kindly let me know, or I'll move on to the next session. Okay, then I'll move on with the next implementation, which is queue implementation. The implementation of queue, I have three main functions. So one is MQ. So here I'm passing an argument called as element and enqueuing it in the queue. So the next is TQ and third one is display. So I have a key which can hold up to 100 elements, and I'm having a maximum size as 3. Initially, now front end rate to be -1. So why do we have two variables? One is for checking insertion path, and the other one is for checking deletion. As this name is front, so in the front we will get deletion tag, right? Because if you people are standing in a queue, the first standing person will get the first bill and he will be leaving out, right? So that leaving out part is called as deletion. So the next is rear. Rear is, it means the end. So at the end or the back, I'm going to insert elements. So that is why I have front and rear. So similar to stack, we have enqueue, dequeue, and display operations. If we need, we can add a store for checking is full. Case files. Give us enqueue or not. Okay. We'll see the coding part for enqueue. As I have already told you, I'll just have an example. Consider this as my initial queue of size 4. and I have to perform these 5 NQs and 5 DQs. And we have content real initially set to -1. For NQing the first element, can check whether your queue is full or not. If your queue is full, obviously you will not be able to add any element, right? So if my queue is not full, I can do whatever operations required. So for checking full, rear or front, anyone might be present at this particular index. I'm checking whether my rear is at maximum -1. So why I'm concentrating on rear is rear is where insertion process is carried out. So that's why I'm checking for rear. Have my rear reach the maximum index it can. If it is true, I'll stop the process or I can continue my process. So next, I'm checking whether my front and rear both are at -1. So why this condition check this? If this is the first element that's going to be inserted into my queue, so this means my front, that is my first element is this, and last element is also the same element. If I have only one element present in my queue, both the first and last element points to the same element present. So in order to assure that, I'm checking whether front and rear are at -1. This means this is my first element into the queue. So I'm just incrementing both front and rear once, that is from -1 to 0, and 96 is being getting added. So next, if I want to add another element, is my queue full? No. Is this my first element? No. So this means just increment your rear alone once and add value at your rear part. So this is what the same thing is done for all values. So and now you can see I have 4 elements. This means my queue is full. So now I want to include another element. Then checking whether my rear has reached maximum index it can. Yes, it has reached the maximum index. So my size is 4. It has reached the index 3. So as this is true, I'm going to print queue overflow and you can't insert or include many element. So next is DQ. So DQ in which order you insert in the same order you will delete the elements. So now the first element that has been enqueued to the queue is -6, so which is available in front. The last element and which has been enqueued to the queue is 71, and that is present with the help of rear index. So now when you dequeue, this front element is getting deleted. So now this should move to first index. So one more condition to check yourself if the queue is empty and you will not be able to delete any elements, right? Because as my queue is empty, I won't have any element to perform deletion. So as my queue empty, no, because my front is not at -1. So front and rear are the same index. So this represents you have only one element present in your queue, and after dequeuing that particular element, the queue will become empty, right? So this is not true. So now I'm printing 96 is my dequeued element and implementing my front. The same day, I'm implementing my front. Again, front implementation. So now we can see is front at -1? No. Is front and rear pointing to the same index? Yes. So this means this is the only one element that is present in the queue. I'm printing this and deleting this element will make my queue empty. So I'm making my front and rear move to -1 in order to assure the empty queue. So now when again a DQ is called, my front is at -1. Since you can print queue overflow and you can't DQ any element. Is it clear? So this is kindly replace that clear. Should I explain anything again? If so, I move on to circular queue implementation. So we haven't, what is this called as, done execution and do that. Before that, we haven't got any NQ, I mean, full assembly conditions. So we'll do that first. So I'll have a void scope. Or even can have if here was at maximum minus one index, which means I use full. So I'll return true. Else I'll return false. This is applicable to MQ also, right? The front is at minus one. So this means this is empty. So that is true. I'm returning one, or else I'm returning 0. Likewise, in main function also, I have if presently also same condition is applicable, right? Presently is true, or you can even have not of the same. So it's one I have 0. So if it puts not so for this true. So I check. I think I forgot to display the answers, right? So it is display no problem. So I'm trying to check was my queue empty. This is not empty, right? Because I have used not there. So this means not of empty is not empty, and this is. I check is my queue empty, yes, my queue is empty. When I'm trying to dequeue an element, we are trying to do underflow, and then add some elements. Displaying it in 45, 34 2, in which order we insert in same order we are accessing it. I mean, when you're just dequeuing it, you can see. So now my queue is empty. When I try to dequeue, it is showing us underflow error. You can see now the result was 3, and when I try to add fourth element is showing queue overflow. Now my queue might be full. I'll check whether my queue is full. Yes, my queue is full. So with that, I'm terminating the program. So next, we will see circular queue. First, we'll see what will be the drawback of queue and why we went for circular queue. So you can see here, also this is a linear queue. So here you have my front at zeroth index and rear at last index. So this means my queue is full. I don't have any space left. Even you can take this has empty slots clearly shown. And in this part, you can see my front as at the second index, rear is third index. So I have some few empty spaces left in the beginning of your queue. Maybe in the third one, you have only one element at the last index, and you have three element empty spaces where three elements can be added. But what happens is when you try to add element to this queue or this queue, so linear queue's drawback is if you even though you have only one element in the queue, but your rear is pointing to the maximum minus one index. So this means my queue is getting full. Even though you have space that has been left in the beginning of the queue, if your rear is at maximum index minus one, then that is not possible. So that is why we implement a wraparound concept called as ring buffer, where when your queue is full, you can just directly wrap to the front of your queue and access your elements. So this is called as wrapping arrow, and that is called as ring buffer. Same similar thing. The only thing what we do extra is can check here. If your front is at zero and rear is at minus one, so this means your queue is full. Or we have another condition. The front is at rear plus one and the queue was full. So all other things are the same thing as applicable. And for DQ, yeah, there is another thing, yeah. When your rear is at maximum index and front is not equal to zero, so this means you have space left in the beginning of your queue. So you can make your rear move to the zero index. So, or else you are just updating in a similar way. And PQ process also, if your front has reached the maximum index it can, what you do is you just wrap around to zero index to get the value deleted. Then display, your front is lesser than or equal to rear. This is normal linear to display path. We are just trying to display from front to rear. Or else you're going to print from front to maximum minus 1 and from 0 to rear. So this is what is the execution of circular queue. I'm trying to enqueue two elements. You can see that my queue is getting filled at the 5 elements. So now when I try to DQ an element, you can find that 23 is deleted and you have 4 elements. You can see that we have 5 elements. Now I'm DQing. My elements are 4. I have 4 elements. So now it means that 0th index is free. So now I try to add another element. So that is getting added towards your end. So when I try to delete another element, 45 is getting deleted, and you can see you have 4 elements, and 33 belongs to 0th index. So if we need, we can just have a look of that too. Maybe here, I'll print this. I'll stop and run it again. Have 0 to 4, and I'm requeuing. Thing I have from 1 to 4. So 0th index is free. So when I try to add another element, you can see that I haven't inserted one. So maybe in the execution that will be seen clearly. My front will be at, sorry, my rear will be at 0 and front is at 1. This is how fusion of circular queue takes place. When anyone have doubts in the execution of queue and circular queue, let me know. I'll explain again. Okay, now we'll see the implementation of double-ended queue. So consider this double-ended queue similar to a linear queue. So I have implemented using linear queues, double-ended queue concept. So I have 2 extra operations, right? So NQ at rear and DQ at front are normal operations. NQ at front and DQ at rear are extra operations. So for these two, for NQing at rear, you'll be incrementing your rear. For DQing at front, you'll be incrementing your front. Whereas for the other 2 operations, you're going to decrement the respective corresponding variables. So for NQing at front, you're going to decrement front, and for DQing at rear, you're going to decrement rear. So that is the only extra operation you're doing. So NQ at rear and DQ at front are same, and NQ at front, you can see here, you are decrementing your front and adding element. For DQ at rear, you are decrementing your rear once. So this is what is the conditions we have to check for. So you can see step by step process. I think I can have display here. And add 23. So front is at 0, rear is at 0. And then 45. And add 6. So I'll check my array size. This is 5. Okay, good. So I'll add 3 more elements also, no problem, right? This is main, right? So now I want to DQ an element. So this is what happens. Now I have to enter an element in the front. So even before the first element 45, I try to add another element. So choice is 3. I give 3 and my element, let it be 77. And you can see front has been decremented once and element has been added. Suppose if you want to DQ a rear, that is as L8 has to be deleted, I have choice 4 and you can see it has been deleted. So this is how a double-ended queue is executed. Faculties, if you have any doubts in the implementation of stack queue, circular queue, and queue, let me know, or else we can wind up the session. Kindly reply so that I can wind up the session and go for feedback fully. And I request you people to switch on your cameras to have photo session. Participants, kindly switch on your cameras to have photo session. So thank you for the session and we can meet up tomorrow. Meanwhile, kindly fill up the attendance sheet which has been circulated in the chat.